Hey, this is Floyd May, and we are doing week number 4 of the Advent of Code event for freeCodeCamp OK. We're just walking through the Advent of Code puzzles for 2021 and hopefully learning some stuff about software development, learning some stuff about some of these interesting algorithms, especially as the puzzles go on throughout the month of December. They start getting a little more hard and they require some finesse in solving them well. A lot of it being you have to find a good way not only to solve the problem but also to solve it in a way that it's going to finish sometime in maybe this year. So, again, my name's Floyd. I'm the owner and principal consultant at a small consultancy called Canyon Trail. I've been doing software development for about 20 years. Um, Today is the second to last event that we're going to be doing for this. But if next week, by chance, you've got one of these puzzles that you just really had a fun time doing and you'd like to talk about your experience with it, the good, the bad, the joy, and the heartache, we'd love to have you on stream. Today, we've got Erich Keil. Did I say that right? Eric's going to be chatting about his day 13 and day 14 solutions with us. He is a freelance designer, developer, project manager. He's not, correct me if I'm wrong here, Eric. It looks like you've not really been writing software professionally, but you're just sort of in the process of learning and growing into a software developer. Is that right?
Yeah, that's pretty accurate. I mean, I've been doing stuff for side projects as part of my work in the entertainment industry, but nothing where I've been legit like the developer part of it is my job. It's been an ancillary tool to the other work I've been doing. So that's
That's
pretty.
really cool. That's really cool. And I think that kind of a skill set and being able to use developer skills outside of an official like software development career. I think that's so undersold and so like it's really really cool for people to be able to do those kinds of things because it makes you come across like a magician.
That has been a fun part of it, and now it's as I'm pivoting into the field, it's kind of interesting because I'm sort of on the flip side of it now. Like I was the wizard who knew how the computers worked, and now I'm like around all of the wizards. And when you're a wizard among wizards, like that's been a fun experience. There's just so much more to learn. It's great.
Yeah. Yeah. Well, and software development really it's a career of learning. Like you never stop learning. And as soon as you stop learning, that's when you stop being effective as a software developer because the industry moves fast and there's always some new problem to solve and there's always a lesson to be learned in there.
Yeah, that's absolutely part of the reason for the pivot. I'm very excited about all of that. Advent Code's
Very
been
cool.
super fun. I've learned a ton doing it. So thanks for pushing this. It's good.
Very cool. And I'm excited to see your day 13 and day 14 solutions. So today, what to expect? We're going to talk about concepts. We're going to talk about the software development fundamentals that go into the solutions that we've built. You're going to see some TypeScript and you're going to see some Python today. I did not build TypeScript and Python solutions for every single day, but I tried to give at least a little bit of coverage on both sides. Most of my stuff's in TypeScript because Python is just a little less comfortable for me to work in. Um, you're going to see unit tests. I think I've got everything through day 18 up on the solutions repository, and everything has unit tests. Part of the reason why you're going to see unit tests, one, is because we as software developers, we need to be writing good tests. And two, those unit tests are kind of the breadcrumbs that I dropped along the way to help you see my problem solving approach as I worked through these problems. Some things it was really, really easy. Some things took some hurt before I could finally get it working. As we've already talked about previous times on this particular event, all of the code that I've been writing is up on GitHub. Our guests, their code has also been up on GitHub. We've got some discussion going on Slack in the Advent of Code channel. What not to expect today? Don't expect a lot of live coding. We're probably going to play around a little bit in the Python interpreter today, just depending on kind of where we go. Don't expect perfection. This is not a highly produced show or something like that. This is just an old software development nerd talking about how much fun he's having doing Advent of Code. Don't expect that there's one true answer. There's a whole lot of different ways to attack these Advent of Code problems. Also, don't expect timely solutions. Today's the 23rd. I have yet to finish anything beyond day 18. Maybe towards the end, we can talk about kind of what strategy I'm thinking about taking for day 19, but we'll just see how much time we have left. Um, if you're working on Advent of Code, you're not alone. If you need help, if you want some guidance, some hints, something like that, Techlahoma Slack's a great place to do that. There's a new thread in the Advent of Code channel for every single day's puzzle. And that thread is usually a great place to get help if you're stuck and don't know what strategy to take. And worst comes to worst, drop a question in there, and somebody will probably help you out. There's a JavaScript channel as well. TypeScript stuff goes there too. Pythonista channel if you need some help with Python. Apparently, my camera is just having itself quite the hissy fit today. Everybody just sort of like look away for a minute, and maybe my camera will, quit being, so afraid of everybody looking at it. There's a template repository up on GitHub. Here's the link. The template repository is there just as a quick start to make it easy for you to get up and running and write tests in watch mode and see that happening. So there's a template for both TypeScript and Python. So regardless of which of those two languages you want to use, it should help you get up and running without a whole lot of trouble. Solutions repository is here. That's where all of my code is. And there's an open PR for Erich's code, and we're going to walk through that stuff as well today. But that's where all of the solutions for my stuff has been as well. I'll tell you right now, day 19 is hard. I read through the solution, or I read through the instructions, and I'm like, okay, I think I know how to solve this, and I just let it just sort of sit in the back of my head for a while, and then just yesterday I was like, aha, there's the key insight I needed. But bear in mind too, like that aha moment is after 20 years of software development. So I mean, I'm 40 now. I've been programming professionally in one form or another since I was 20. That's a lot of years, and these puzzles are hard. So don't feel bad if you're struggling with them. Don't feel bad if you're having a hard time with them, because they're meant to challenge. They're meant to be tough. All right. So last week we finished up through day 11. So let's talk about day 12. Day 12, let's embiggen the font here. Get rid of that. And Kimberly, font size check.
I think we're okay. A little bit bigger would probably be a little bit better.
One more time. There we go. Cool. Yes? Okay. So day 12, let's go take a look at that here. So if you, like me, maybe a little farther ahead than day 12, or maybe you haven't gotten to day 12. So let's sort of walk back through what is day 12. You have a cave system where you've got connections between caves, excuse me, that that are your puzzle input. So the idea is you've got a cave system and you want to build a map of it like this right here, not necessarily in ASCII art like they've done right here, but you need some sort of data structure to represent this cave system. And then you've got to figure out how many different paths are there from start to end in this cave system. And you've got the capital letters, which means these are big caves and you can visit them as many times as you want. And then you've got the small letters, that means you can visit them only once. The part two of this one gives you a little twist on how many times you can visit a single small cave. So let's talk about this a little bit. First off, this is a graph algorithm thing. What does that mean? Well, a graph is a mathematical / computer science concept where you have nodes and edges. So if you look at this little ASCII art diagram here, start, end, A, B, C, and D. These are nodes, and then the lines between them, these are edges. And because it doesn't matter which direction you go from one node to the next, this is what's called an undirected graph. Some graphs are directed, which means there's like an arrow instead of just a line between the nodes, and you can only follow the arrows in the direction that they point. So let's talk about, here's what my solution for this looks like. So I did day 12 in TypeScript, and I have this cave class. We're going to go object-oriented programming, and it gives us these little bits of information about the cave. What's its name? Is it the start cave? Is it the end cave? And is it a small cave? Because small caves we treat differently than big caves. And then we have this thing called a cave map. So this cave map is what keeps track of and builds this graph data structure for us. So our connections are records. So in TypeScript, a record is basically just a hash map where this is your key type, so our keys are strings, and then the value is this type. In this case, it's a set of strings. And then our caves is just a map of the name of the cave to this cave object that gives us this information about it. Now, one of the things that you'll notice is that this connections for every one cave, that cave can be connected to many other caves. So that's why this connections thing is shaped the way that it is. Now, we parse our entry, cave one name, cave two name, and I've got this get or add cave, which goes and looks for our caves and then adds that cave's connections to this connections object. Excuse me. Then, once we have our caves, we add the cave 2 to cave 1's connections, and we add cave 1 to cave 2's connections. Why are we doing this? This is an undirected graph. It's an undirected graph, which means we can go either direction. So anytime you see a connection between two caves, you know you can go this direction or you can go that direction, which is why we have to add the connections in both directions. We'll see why this works here in just a second. Then, here, what I'm going to do is I'm going to skip past this. I have this find paths function. So find paths, just for part 1 and part 2, find paths, we just hand it the cave map, which we just built, and we tell it, we do this find paths. So we create one of these candidate paths for our cave map, and then pass along whether or not it's part 2, which we'll talk about here in a second. And then we ask it to find paths. So find all the paths through the cave. So this candidate path object, it starts with the path just at start, because that's where we start. Then when we ask it to find paths, it's going to give us an array of string arrays, so an array of arrays. So these are all the paths. So our current is whatever the last thing in our path array is. And so in this case, when we've just started, it's start. So if current is end, then we know, okay, we found the end of the path. Then we've got to find out what are the potential places that we can go from where we're at here, from current to somewhere else. So let's find what are our visible caves. So we're going to go look at all of the connections for wherever we are currently, go get the cave objects and figure out, can we visit this? So let's go look at can visit. So we can't go back to the start cave. That was against the rules. If the cave isn't small, we can visit it as often as we want, as many times as we want. If we've never visited it, we can visit it. And if it's part 2 and the revisited cave has not been set yet, so we'll talk about this here. Let's go ahead and talk about that now. So for part 2, we're allowed to visit a small cave once, or we're allowed to visit a small cave, a single small cave, at most twice. So it means that for any given path, a small cave can appear up to 2 times, but only one. So what we're doing is we're keeping track of which one of those small caves did we visit twice. So in this can visit, if it's part 2 and we haven't revisited a small cave yet, we're going to say, okay, we can visit that one. Otherwise, we can't visit it. So now, find paths. We know what all of our visitable caves are. For each of those, we're going to make a new candidate path, and we're going to set that path array to one more for that cave. So we start with a path of just start, and then we have 3 or 4 paths depending on how many connections we have out from start, and those paths are a little bit longer. And then those paths are a little bit longer, and then they get a little bit longer, and then they get a little bit longer, because what we're doing here is recursively calling find paths. So what we get at the end of this here is a string array, because we've got all of the paths from all of the caves, from all of the visitable caves that we're doing here. And then what we're doing is just flattening it back out to give us an array of array. So then way back down here, we call find paths, and we just ask, what's the length of this? What's the length of all of these paths that we just figured out? And that's it. Now let's talk about the tests for this. So this, hey, look at that. That says day 1. It should say day 12. So these expected paths, so this is from our sample input. I believe sample input 1. And we're sorting these. Why? The reason why is because we're not quite sure what order they're going to come back in. So we're going to call this find paths function on sample input 1. And then we're going to take each of those paths and turn it into a string where everything is separated by commas so that it matches up like this. And so we're going to sort them both the same way, and then we're going to expect them to be equal. So this gives us an opportunity to sort of peek inside of when we walk through all of the potential paths, are we getting the same data that we expect? Because if I believe in the instructions, it gives us all of those paths. Yeah. So this right here is exactly the same as this right here. So what we're doing is we're just walking through and saying, does it give me all of the same paths through this cave system that that the instructions said I should find? So this gives me some confidence that my pathing algorithm is working pretty well. Okay. And then I walk through the sample input 1, sample input 2, sample input 3 because it gives us multiple different sets of sample input. And those all worked just fine. So then part 1. So once I had those put in place, I got my part 1 solution, then did my tweaks for the part 2. Works great. So that's it. Kimberly, do we have any questions or comments on the Twitch stream?
Not really. People are just talking about doing this because it's fun. We do have someone watching on the phone, and so you might bump up the font size even more because this is pretty small to read on the phone.
Gotcha. I don't know that we can do a whole lot more on the font size because that's going to be really hard to read on a phone anyway. I've tried to look at code samples on phones and it's hard. So let's see. Wow, yeah, I can't do that.
Okay.
Can we
This is
compromise
all
right
on.
here?
Yeah, that'll work, and it's also on GitHub.
Yes, good point. Very good point. All right, so let's talk about day 13. And so what I'm going to do is I'm going to pull up your pull request, Eric, and let's talk about day 13. So day 13, go. Aha, transparent origami. So this was a really neat problem. The idea behind the problem is you have a really big sheet of paper and you're given instructions to fold this sheet of paper at certain spots, and then there are points on the paper, and we're supposed to figure out when you fold the paper, do those points overlap? And where they do, we only count them once instead of twice because they overlap. And how many points total do we have? So Eric, um, thanks for being on stream with us today. Talk me through your day 13 solution. What were some key insights that you found? What were the hard parts for you? Just tell the story of how you figured out day 13.
Sure, yeah. I mean, on some part, all of this has been hard for me because, like, I wrote my first jest test on day 6. Day 1 was my first like node project running in the terminal because I've been working in JavaScript now, and my background is in other stuff. So that's where I started from. The puzzle here, I love geometry stuff. So coming from a design background, like I was really excited about this one. It was clever. And so, living immediately go to this like idea of thinking of an XY grid. And one of the things I noted in the instructions that was sort of a key thing I had to figure out how to handle was that the points needed to be discrete, right? You couldn't have duplicate coordinates. If you folded the transparent paper on itself and 2 points condensed, you should only end up with one iteration of that point in your resulting set. And
Yeah.
I tried some sort of brute force ways to do that initially that were really inefficient. And then I had the learning curve of dealing with set. I went to a set, right, as a thing that enforces unique values. But of course, as some of my fellow newbies may have learned, right? If you do if I'm thinking in XY coordinates and looking at either like a two size array or an XY object sort of setup, that because all those things are stored as references, you can't do a simple equality check in a set. Like you can get the same point returned if you just store those as points that way. So I took the approach to create a map of all the X coordinates as keys. So I was essentially storing columns in the map and then using the value for each of those X coordinate keys as a set. So that way every pair could only exist once. And then when that unlocked for me, I went, oh, then the folds become really simple, because if you're folding across the, with the Y coordinate, so you're doing a horizontal fold, all you have to do is iterate through all the values and mirror them across the fold line. And if you're folding vertically, you can iterate through the keys and mirror them across the fold line, and the sets will condense on their own.
Okay.
So that's basically the approach I took to do that.
Okay, so walk me through your implementation, or if it would be more useful, we can look at your tests to sort of see your problem solving approach.
Yeah, I can walk through the implementation. So I started with just trying to write a little parsing function that took the input and returned an object of dots and folds. So the parse input's going to be down at the bottom.
Yeah, I feel like I saw that parsing. Yeah, here it is. Okay.
Yeah, so I've got the parse input function there, which just it's broken down into really discrete steps instead of doing a ton of chaining to help my brain get better at figuring out the parsing bit. So we take the input and we break it down into its individual lines, and then based on figuring out where the empty line break was between the folding instructions and the coordinate points, I basically broke that out into 2 bits. So I have a list of the fold line instructions and a list of all the dot coordinates. And then I took those and ran them through that for loop there, which goes through each dot line, splits it to get the X and Y coordinates, and then creates that XY map. So if the X coordinate already exists, it adds the Y value to the existing set. And if the X coordinate doesn't exist yet, it creates it.
Okay. Cool. So you've got so in order to get to a point, you've got an array of, or a map of X coordinate to set of Y coordinate.
Correct.
So you've basically got a nested map.
Yep.
Awesome. Okay. And that's a really interesting way to tackle that. Okay. So given that, then you have your Y coordinates. So when you fold on a Y coordinate, you're basically you're taking the X coordinates that are beyond the fold and merging them in. So you're just doing a set merge of.
Yeah, that's all in the fold dots function, which I think is right there above parse inputs. So that function just takes a dot and returns it. It takes the dots and the array of fold instructions and returns the mirrored dots. So depending on whether it's an X or a Y fold, it executes that little block there that does what you just described.
Okay, cool, very cool. So one of the things that I did, now I can't remember, did I do this in Python or did I do this in TypeScript? So, but before we look at my solution, because I think seeing some compare and contrast can be really, really helpful. You touched on something that I feel like trips up a lot of programmers, and it's this notion of equality. So here, let me pull up a command line window, and let's play with equality in JavaScript, because this trips up so many people, and it's such a frustrating situation. So let me embiggen Mr. Font here.
Yeah, I knew as soon as I ran into it what the problem was, but even I didn't think about it up front. But, oh yeah, I'll just store these as a set of points, and as soon as it didn't work, I knew why it wouldn't.
Let me just do that. Do one more here. All right. So, all right. Do this, and then we're just going to do node. Okay. So equality. So let's talk about this. So if we have we've got a set, and then my set dot add. So let's just do like a X at 0, Y at 4. So now we have a set, and so my set dot length. Wait, it's size, not length, isn't it? So my set size is 1. So now if I add a new object with the same data, the set size is 2, even though we've got 2 copies of the same piece of data. So this is the whole equality thing, right?
Mhm.
And JavaScript is not a great language, and TypeScript the same way, not a great language for sort of custom defining equality. And it also doesn't do this thing that Python does, which for a lot of your sort of primitive types, it like just automatically giving you equality functions. So let's go play with Python for now. Uh, so in Python, we can do something really, really interesting. So let's run Mr. Python interpreter. So as you can tell, I'm not much of a Pythonista. So now we've got a set. So so let's add a tuple of x and y, or actually let's add a dictionary. Since you did sort of nested dictionaries, or really like nested sets, or nested maps, let's do that. So my set dot add x 0 y 4 unhashable type. Oh, yep, we can't do that in Python because that's not hashable. But what a great example we're setting so far. So and really for something like Python, a tuple is probably more more Pythonic.
Mhm.
So so the length of the set is 1 after that first add instruction. So now I did the same add instruction. The length is still 1. So our tuple, it compares for equality item by item. And so this kind of problem in Python is kind of I feel like a whole lot easier to solve, because you get this sort of equality behavior for ordered pairs like this a whole lot easier. So if you map your coordinates as a tuple in Python, this gets a lot easier.
Yep, I had exactly that thought when I was halfway into figuring out how to use a nested map to make it do that without me having to write custom equality checks.
Yeah. So now the great mystery is, what did I do with day 13? Did I do Python? Yes, I did Python, because I saw that and I was like, I immediately recognized this will suck less in Python. So let's look at day 13 in Python. And you go away, go away, go away. All right, cool. Oh yes, 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 yes. Okay, so this is an interesting thing. The way I tackled this problem was so parsing function here. The way I did this is, so I've got my raw coordinates and I've got my raw fold. So these are just the strings that contain the instructions. So I split my entire input on 2 new lines. So that's how I got section 1, section 2, basically. And then my folds and my coordinates, just, I mean, pretty uninteresting code there. But what I did is I turned my folds into these transform objects. So what is a transform object? It What it does is it sets an X threshold or a Y threshold, depending on whether it's a fold along the X or a fold along the Y. And then this apply transform, what it does is it gives you a new coordinate based on having done the fold. So for instance, if you've got a fold at X equals 100, any point that has an X coordinate less than 100, nothing happens to it. It stays in the exact same place. It's only when you get past the fold that a transformation should take place, right? So you do a fold and you have something beyond 100, then the new X is going to be this. You're going to go um, the X threshold minus the difference between X and the threshold. So that's how you get your new X. Now, what's interesting about this is that we can take these transforms and stack them up. And so we can push a point through this transform, and then the next transform, and then the next transform, and then the next transform, and we get that point's final position. So then what we can do, we can make a set of all of the folds. Okay, so part one, we just do one fold. For part two, I have this apply transforms function, which really just takes my coordinates and pushes them through all of the transforms. And then I take a set of those, and then that gives me all of my unique stuff. And then for each of these, I forget how part two worked, but at the end of it, it's this it's this set and the point equality that really makes this elegant in Python. Um, point like Python being able to treat tuples and strings and lists as equal to one another makes this go so much easier than doing it in TypeScript. If I were to do it in TypeScript or JavaScript, probably what I would have done is I would have used a set, but I would have, instead of putting objects into the set, I would have put strings into the set. So I would have taken part like the x coordinate and a comma and the y coordinate. I would have put that string into the set.
How did you end up handling the display for part two of getting the letters out of the points? Out of curiosity.
That's right. That's right. That was the cute part about part two. Is you have the display here, and let me go ahead and run my part two. Wait, that's day 14. Supposed to be not day 100. I'm a programmer. I type for a living. I can do this. So this is how it looks, and I just did X's and spaces. Okay, so here's what I did. So I needed to know what the width and the height was in order to figure out how much spacing to create. And then so for each y, so starting at 0 and going up, for each y and then for each x, I just made a string that ends in new line. And then if there's a point in um, in my set for x and y, and again, we're inventing a brand new tuple and saying, hey, do you brand new tuple exist in this set? Yes or no? That only works because Python's like this tuple is equal to that tuple if they contain the same stuff. So x if it's in the set, otherwise a space. And then just over and over until
I was super hacky with that. I used console.table and printed it out as tabular data. So it rendered the letters for me out of an array of letters.
nice. I like that. I like that a lot. I don't know that I've ever used console.table.
I remembered it existed from some weird thing I did once, like forever ago. I was like, wait, there's a way that the node console will spit out tabular data if I get it formatted right. So
Okay, cool. So let's look at day 14. Here we are, 14. Okay, polymerization. Okay, this one was cute. This one was really neat, and there was a lot of opportunities to like get yourself into an infinite recursion problem or infinite loops or like this one was really interesting. So you have a polymer, which is just a sequence of letters, and then you have these replacement rules. So when you see these two letters together, you're going to insert a B in between them. When you see these two letters together, you're going to insert an N in between them. So let's go look at your day 14 solution, Eric, and let's talk about your so tell me the story. Help like
yeah, this one.
the
So
joy and the pain.
this I wasn't sure on this one what they were going to ask in part two, and so I was concerned that there was going to be that part of the level up was going to be we were going to need an indexed version of the polymer, right? Like we were going to need to know the actual string and not just counts of elements. So the
Mhm,
first run through part one, I literally iterated the string and was able to spit out the final polymer. And it
mhm.
became very clear immediately on the data set for part two with that exponential growth that that wouldn't finish this year in the way I was handling it. So I ended up redoing, I came up with a solution that worked well for part two, and actually then just mapped it directly onto part one with no changes out of curiosity. And it like worked, since I knew we only needed the total count of the existing elements in the string. So yeah, essentially what I did here was break the operation down that happened at each simultaneous insertion step to the idea that we took each overlapping pair of elements, we fractured that pair and essentially destroyed it, and replaced it with two new pairs, which was the start element plus the new added element per insertion rules, and then the new element plus the tail. So basically walking through the approach was to we'd get all the pairs. So we'd get an array of the overlapping consecutive string pairs. We'd get a map of the rules based on parsing the insertion rules from the input. And then I initialized an object.
Tell me where to scroll here, because
Yeah. So let's go down to knitcounts line 65, I think is where it is. Now that I'm at
okay, cool.
Yeah.
There we go.
So this is where we essentially initialize what our starting polymer is. So we call that get pairs function, which just parses the line to get us an array of the pairs we're starting from. And then for each pair we create this new element, and we create two new pairs. So we split the existing pair and create the two new pairs and populate that seed object with that format there. And then when we increment the polymer, the next function down there, that increment poly, for the simultaneous insertion, what we do is go through and get the existing element counts. So what I'm storing is for the existing polymer is a count in a map of all the pairs.
Okay.
And I'm storing a count of all the individual discrete elements. So that's essentially the object in which I'm storing the existing polymer. So when we increment that, we go through, we create an array of all the existing pairs and an array of all the existing elements based on their string length, since they're either twos or ones. And then for each element, we populate our new poly that we're going to return gets populated with the existing counts we started from, because we haven't lost any elements, we've only lost pairs. And then we iterate through the pair count, and for each pair we remove that, where we populate the new polymer with the two new pairs created by the new element insertion, and increase the element count. So you can see there at the bottom, we iterate over those three keys, the two new pairs and the new element, and then that returns a new version of that object that has the new updated pair counts and element counts. And so that functions then for both part one and part two.
Interesting. So for each step in the algorithm, you're basically just growing that hash of this pair has these many individual elements in it, and then when you bust that apart, you're going to bust it apart into another pair of keys in the same object.
Yeah. So the increment poly takes the existing polymer and returns a new one back that has an updated count of the existing pairs and the existing individual elements that make those up.
Very neat. Very neat. That's a really, really interesting solution. I went very literal with mine, and I'll tell you, I struggled pretty hard with it because um, I didn't know where part two was going either, so I kept the string of polymer the way that it was, and I think I did day 14 in Python as well. And if I had it to do over again, I probably would have done something probably more similar to yours. So let's look at my day 14. What did I do here? Okay. So this was an interesting thing. So the problem that I had with part two is that it was CPU bound. Meaning it took too much CPU effort to compute every possible expansion. Because what you're going to wind up doing is, so let's say you've got the string. Oh, not that. Where do we go? So let's say you've got the string NN, and there's a rule for NN. NN will give you NCN. And then what was part two? Part two said,
I think it just escalated to 40 steps.
Right. Right. So the thing with part 2 that you had to understand is that NN for step 1 produces NCN at step or NN at step 0 or at step 1 produces NCN, and eventually you're going to wind up with another NN in here somewhere. And what I discovered was that if you memoize, so memoization. So what does that mean? That means you have a function, you call the function, you get a result, right? Calling that function may cost some sort of CPU time, or it costs a trip to the database or something like that. So memoizing would be, I have a function, and that function will say, have I seen this pair of arguments before? Have I seen the arguments that I'm looking at right now before? And if so, I'm going to use a cached result rather than go recompute it over and over and over and over and over. So by memoizing, that's how I was able to tackle part 2. And so talk me through for part 2. How did you get past that performance hit?
Well, because I was, this actually kind of took me back to the lanternfish example you gave us a while back, because all I was actually tracking was the quantities of
Mhm.
existing pairs and elements. My computation hit really didn't get bigger because I wasn't the value I was iterating on really didn't grow that much. The counts grew within the object, but the number of new pairs were pretty limited by the rule set. So my object only ever had a dozen or 14 keys in it. Um,
Okay. So you went full lanternfish on this. Yeah, you see, I didn't learn my lesson from the lanternfish thing, and I did it the hard way.
I did it. So to be clear, I did part 1 the hard way the first time, hit the performance hit, and went, "That's not going to work." Oh wait, lanternfish, and I rebuilt it. And went, "This will solve this." And thank God they didn't ask for like a segment of the string in part 2. I think that had I had to do that, I would have figured out a way to add an indexing to the object I was storing. So I would have had a way to rebuild the string at the end. But
So let me show you what I did with part 2, or just this in general. So, um, I I actually built the dang polymer step by step by step by painstaking step. So here are my tests, and so given this start input, I wanted to do a run step and make sure I get the output I expected. Okay, great. Um, then the whole idea behind this was I wanted to make sure that my insertion rules were working, and then I just optimized and optimized and optimized. I finally discovered what my problem was with the whole memoization problem. So I have this insert polymer function that takes the starting polymer and the set of rules and the count for how many times to run it, and this this memo, which is just an empty dictionary for right now. And then what I'll do is my key for the dictionary is whatever the polymer is and the count. So, for instance, um, if I've if I've got to do 40 insertions and I've got a string of AABC or whatever at 20 steps in. If that same AABC shows up at 20 steps in somewhere else, I don't have to recompute all of that. I can just get it immediately. And then, so this is an interesting thing as well. So this itertools.pairwise. So itertools is a Python library that gives you lazy iteration stuff. Now this pairwise thing, this works very, very similar to zip, which we've talked about in the past handful of weeks. So you give it a list of stuff, and it gives you all of the pairs. So for instance, if I do pairwise on the string AABC, it's going to give me a tuple AA, and it's going to give me a tuple AB, and then it's going to give me a tuple BC. So what that does is it gives me those pairs that I can then test against my rules. Now, the interesting thing about this is when I do a single step on my rules, um, the polymer that gets produced, I do these pairwise, and then I get whatever gets inserted. So for instance, when I've got AB in pairwise, so what gets inserted is the left-hand side plus whatever gets inserted, but I'm not adding the right-hand side. Why? Because the next pair is going to have the right-hand side. So for the first pair, A is the very left-hand part of the string. Then for the second pair, A is going to be the right-hand side of that first pair. So I just use the first one over and over and over again whenever I expand it out, and then I tack in the last one excuse me, at the very end. Now, I believe, did I retire this one? Yeah. So this was the naive version. So this one worked fine for part 1. It blew up horribly in part 2. So I'm not actually even using this function anywhere. I'm using this function, which works almost exactly the same way, except I'm using memoization. So I'm memoizing the results. And honestly, like this was just a mess. And I did not do a great job with it.
I'm really
Um,
glad I didn't really have my head wrapped around memoization yet, or I would have fallen right into that same trap because literally the journey you just described was exactly where I was when I was like, I have to do something completely different because I don't know how to optimize my way out of this hole. I have to do something else. Newbie luck.
I just kept pounding that square peg into the round hole, and I got it to work, and it was neat. Um, so for left right, so here's my pairwise thing again. Then I have this. What did I do with this merge counts? What is merge counts? Let's go have a look. Yeah. Okay. So this is basically just merging the dictionaries. Um, of these counts. So yeah, so I'm just returning the counts, but I'm actually still yeah. So in effect, what I'm doing is basically for part 2 the exact same thing that you did. So I lied a minute ago and said, yeah, I made the whole polymer. I didn't.
I feel like it's really hard to make that whole polymer with that growth at 40 steps. It's going to be a gigantic
Yes.
string. I was running into memory exception issues and all kinds of things.
Yep. Yep. So I'm basically doing the exact same thing that you did. So part of this is me sort of remembering the heartache of going through day 14. So let's talk about day 15 now. No. Let's see, day 15. So Eric, you had said that you're still kind of halfway through day 15.
Yeah, I got all of the tests to work for part 1. Like, I mean, all the samples return the correct answers, and so like I know my algorithm technically will get to a right answer, but
Mhm.
the issue I'm currently having just with my current knowledge base of like the this is to me is another graph traversal problem, and it's you mentioned the Dijkstra algorithm, so it's the ability to limit the search, which is the same problem I ran into on part 2 of 12. Day
Mhm.
12 is that right now I have my program will run, and if I give it a couple of years, it will calculate all of the paths and then filter out the ones that are valid, and I need it to be limiting the search along the way because obviously that is just not performative enough. So that's where I'm at
Right.
on it currently.
Right. So so I have a part I have a solution for day 15, and I'll show it to you here in a minute. Um so this really is what we're trying to do is we're trying to get the top left to bottom right, and we're trying to accumulate the smallest amount of numbers as possible. But the thing is, and this is one of those tricky algorithms, because you could you could have a 9 somewhere that requires that would actually have a better path if you just routed around the 9 instead of straight through it. So it's not a matter of just going down and to the right mostly. Really, it's an issue of just finding the route with the lowest cost. And turns out I forget how long ago this algorithm was built, but this was one of the founding fathers of computer science, Edgar Dijkstra. And when you hear it pronounced and then you go to read it, it sounds weird, and I forget what his nationality is, but it's Dijkstra. So,
It's got to be
whoops,
Scandinavian.
yeah, Dijkstra. So that's pronounced Dijkstra. Um, And this is an algorithm for finding, so you've got a graph. We talked about graphs a little while ago. For finding from one point of the graph to another the shortest path. So if each edge of the graph is a length, we want to go the least amount of length. So originally this algorithm was about finding the best paths between cities given the length of the roads between the cities. Um, and this problem for day 15, this is a great application of Dijkstra's algorithm if, especially, you can handle the case where that grid gets really, really big, optimizing this. Because the way this algorithm works and the way we would apply it here, so the length from here to here, so from 0, 0 to 1, 1 here, the length would be 3. So we would treat it in the algorithm as a length of 3. So then from here to there, that length would be, if we were to take that path from just diagonally, that length would be 6 because we went from here and accumulated 3. We went there, accumulated 3. Um, looks like, no, never mind. Now, the interesting part about this is Dijkstra's algorithm tackles part one really, really easily. Let me, yep, I did Python for day 15. Save map, mapping state. Aha, okay. So Dijkstra's algorithm is all about keeping track of which things have you visited and what's the running total of the length that you've accumulated for everything that's just past one from where you've visited. Um, then you take the next step of the algorithm based on where's the smallest distance. So for part two of day 15, you have this grid, and the grid gets way, 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 way bigger. So how much bigger was it? I forget. Yeah, it's huge. So it's like 100 by 100, or it's 500 by 500, which is 250,000 cells. Um, so we don't want to do a traversal brute force through 250,000 positions. Now the challenge with it is as you start from the top left up here and you sort of work your way out looking for that shortest path, the edges of where the algorithm has reached will start to like the length of those edges is going to start to get really, really long because you've got lots and 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 lots of possibilities that you still have to keep up with. Um, so my day 15 solution uses Dijkstra's algorithm, but I have this mapping state object. And really, the only thing this mapping state object is doing is it's keeping track of what are the distances that I've computed for each of the intermediate hops. And I'm using a heap data structure, which a heap basically does a really good job of efficiently giving you either the minimum or the maximum value from all of the data that you've put into it. So what this means is at each step of the algorithm, rather than iterating over all of those things that I've already computed the length for just to find the smallest one, I can do it in constant time. So when I say constant time, that means um, if the size of my data is 100, it costs me the same amount of CPU time to get the smallest one as if the size of my data was 1,000 or 10,000 or a million. Now, what constant time means is that's really, really good because instead of having to iterate over all of that stuff, it's really, really quick. Now, the naive implementation of Dijkstra's algorithm is gonna be so this right here. So get the position that's at the minimum distance so far. So the naive version of Dijkstra's algorithm is going to look at all of the nodes that we've looked at so far and find the minimum, and that costs however many nodes you've got. So using a heap here for Dijkstra's algorithm really makes a big difference. It's a great lesson in understanding the algorithm. It's a great lesson in learning how to optimize that algorithm. Again, my implementation here is in Python, and then there's this heap Q library that's a built-in for Python. That's how I'm doing the heap operations. I didn't want to write it myself. Wouldn't recommend writing it yourself unless you just want to, learn how a min heap or a max heap works. Um, it is 12:55, and I'm debating whether or not to go ahead and get into day 16. But actually, we're gonna take a weird path to day 16. Um, sure, let's have fun with it. Let's do this. So, in my humble opinion, I feel like day 18 and day 16 need to be swapped because I feel like day 16 was harder than 18. And if you have the skills that you would need to tackle day 18, it would be kind of a stepping stone up to tackle day 16. I did them in the opposite order and I had a bunch of problems. And part of that is because of the way that I chose to do both of those problems. So let me show you what I did, and then we'll probably spend a little bit more time next week talking about this. But I'm just gonna have fun, and we may even go over time a little bit, Kimberly, if I'm not keeping you from something. All right, so let's talk about day 18. So day 18, the snailfish numbers. So this was cute. This was really really interesting. Um, you have this deeply nested sets of pairs, and then you have all of these rules in how to combine the pairs together to do mathematical stuff. Now, what I did with this is I used what's called a parser combinator library. So what does that mean? That means it gives you a set of functions that you can use to build a parser. And parser combinators are really, really handy, especially when you have recursive data structures like this. So this is a pair that can have pairs, that can have pairs, that can have pairs, that can have pairs nested inside of it infinitely. Well, not infinitely, but recursively for arbitrary depth, however deep you want to go. So what I did for this guy, and then day 18. First off, I set up my types, and I'm a big fan of type systems. Type systems do a great job of making things that could be runtime errors into compile time errors. And that I think is great because it makes it harder for you to write code that breaks. So I have a snailfish number, and that's either a pair or a regular number. And the reason why I have this regular number thing is because I'm actually doing the opposite thing that we talked about with equality. um, I actually want if there's an 8 over here in this spot in a snailfish number, I don't want that to be treated the same as an 8 over here in this other spot in a snailfish number, and I'll show you why here in a little bit. Um, but if you look at this gives me the ability to describe a snailfish number in a completely precise way all the way down. So, um, a pair has a snailfish number on the left and on the right, and it has a depth. And then I use this tag so that I can easily differentiate. What kind of thing do I have? Do I have a pair or do I have a regular number? Now, this library TypeScript parsec. So this is a parser combinator library for TypeScript. And one of the things that it does is it builds a lexer. So what's a lexer? A lexer is just a thing that cuts a string up into tokens. And sometimes tokens are a single character, sometimes they're a lot of characters. So for instance, I'm using a regular expression here on line 13 to turn any series of one or more digits into a token called a number. And then I'm parsing left brace, right brace, and comma, since that's the only stuff that can show up in a snailfish number. And then I've got these, anything that starts with a P is a parsing function. So P number, so what I'm doing is I'm saying, when I get a token that's a number, turn this into a a snailfish number. So my tag of num right here, and then I'm parsing the text of that token into an integer. So my value is this number. So that's what this is right here. So then a pair, I parse it as a token, and then an alternate. This alt says try the first one, and if it doesn't work, try the second one. So I'm going to try and see if it's a number, and if not, then I'm going to try to parse it as a pair with a depth plus one. And then I did this p late bound because, and this is fun. Um, if I define you parse a pair at a given depth by trying to parse a given pair at depth plus one, you'll get infinite recursion there, and that's bad. But if you do it late bound, it won't actually do this addition and descend until it's actually attempting to parse something rather than doing it right now when you're defining it. So for this sequence of left brace, either a number or a nested pair, comma, number, nested pair, and then right brace. So we've got 1, 2, 3, 4, 5 things. So then I've got my pair. So remember zero-based indexing. So here are the results from all of those subparsers. So I don't care about 0 because I know it's a left brace. I care about the result of this. So that's 1. I don't care about the comma, which is at index 2. I care about the result of this at 3, and then I don't care about this. So 0, don't care. 1, I care. 2, don't care. 3, I care. So 1 and 3. So that's how I get a pair. Now, I also defined this guy right here. So this SN object. So I took pattern after this from how we deal with JSON in JavaScript. Um, so JSON.parse, JSON.stringify, and then you remember this magnitude function from day 18. This just computes the magnitude of a snailfish number, and it does it recursively. Then really the fun part about this is once we parse a snailfish number, we've got all of these things that we need to be able to do with it. So for day 18, we've got to add stuff. So you take one number and the other number, and you make a pair of those numbers, and then you reduce them. So this reducing thing, this was kind of a big deal for snailfish numbers. So let me show you how I handled reducing snailfish numbers. Reduce step. Where is reduce step? Here we are. Okay. So find explodable. So what is find explodable? So if you remember, an explodable is a pair that's nested 4 deep. So going and finding something that's explodable, where did it go? What it does is it's a recursive algorithm. So you know it's recursive because I'm calling find explodable inside of find explodable. So if it's a number, we know it can't possibly be a pair that needs to be exploded. If its depth is less than 4, and this depth thing is really, really neat. This is really, really interesting because I'm keeping track of the depths all the way down. So if you remember back to our parser, we're setting the depth. So as deeply nested as it is, that's what the depth is. So this find explodable, if the depth is less than 4, then we need to keep looking on the left side and on the right side of this pair that we're looking at. And so once we get to the depth of 4, we just return that pair. This works because the instructions promised us anytime you have a pair that's nested 4 deep, it's guaranteed to be a number and a number. It's not going to be a nested pair on either side. So we find the explodable. Where did explode go? Here we go. So to reduce it one step, we find the explodable, and if it's not null, we do the explode operation. So we have left, right. Then what I did is I made a list of all the numbers. So this is really, really inefficient. Um, but it works really, really well because if I've got a number to the left, I know how to find it. And this is really, really important because I have this replace node function. So Eric, you remember um, we were talking about equality and how equality works in JavaScript, right? Now, my snailfish numbers, where are we at here? So let's go play around in Node for a minute. Nope, I can't do that. Um, so my snailfish numbers had stuff that looked like this. So it was a tag of num and value of 2. So let n2 equal something that looks very, very similar to that. So n1 equal to n2, that's false, right? Now, this actually works out really, really well for us here because, for instance, let's say I want to replace n1 in a nested snailfish number structure. I want to replace that with something different. So, if I have that specific actual thing, that works really, really well because if I have a snailfish number, say that has a 2 over here on the left and it has a 2 way over here on the right, the only one that I want to fiddle with is this 2 over here on the left. So if I have a left-hand side number to replace, so if you remember this, the whole explode thing, you take the left thing of the pair and you add it to the number to the left. You take the right thing of the pair, you add it to the number to the right. So here is the number that I want to replace. Here is the replacement that I want to put in there, and then I'm going to use this replace node function. So the root here is the snailfish number that I'm looking at, and if this one is equal to the existing one, we're going to return the replacement for it. So this only works if it's the exact same number, not a number that has the same value, but the exact same thing, which is why I didn't just use numbers. I used this sort of wrapped object because this replace node function helps me do this explode operation really, really easily. So I do replace node once, replace node twice for the left side, the right side, and it only replaces those things in this nested structure. And then I have to refine my explodable because I've rewritten it. Why? Because replace node rewrites things and then recursively calls replace node. So I have to go refine the explodable after I've done these replaces, and then I replace the explodable with a number with a value of 0. So that I feel like was the hardest part about day 18, but um, the big deal for day 18, which I feel like made a huge difference for me, is I didn't have to think about or care about how do I turn these numbers into a data structure because this Parser Combinator library did all of that for me. I didn't have to worry about like array index position while I'm like, okay, I've got this left brace here and like how many positions past it is the comma or anything like that. I just have to say parsing a pair is a sequence of left brace, number or pair, comma, number or pair, right brace. Done. Now, for day 16, which we'll probably revisit day 16 a little bit next week on stream, I used the same parser combinator library to deal with day 16, but there were some optimizations that I had to add to it. And so I'm actually probably going to wind up sending some pull requests to TypeScript Parsec because they have some really important things missing that keep this from blowing up. But the interesting thing about this is you get this bit stream, and then you have all of these rules on turning this bit stream into a nested packet structure. It's very, very similar to the whole snailfish number thing from day 18. So I used a parser combinator library to do day 16 as well. Not 15, 16. That one. So again, here are my types. I have a packet, which is either a literal packet or an operator packet. And these operator packets, they have these operations, and those are our operations. And then I've got, parse bit sequence, parse bit, parse number of a given width, so on, and then all the way down here, so an operator packet is going to be a number that's 3 bits long. We're going to parse the operator, and then we're going to figure out how to parse the subpackets. So very, very similar. We're 10 minutes over time, so I'm going to go ahead and wrap up here. I want to talk a little bit more about my day 16 solution next week, but I don't want to get way too deep into it because it definitely gets pretty heady into parser combinators and how they work. But honestly, I had a whole lot of fun just sort of figuring out, okay, how does this library work? How do I force it to do what I want? But the neat thing about using a parser combinator library like this is that if you can parse it into a data structure that looks like this, then all of the operations that you have to do once you have it into a data structure become a whole lot easier to deal with because instead of dealing with a sequence of ones and zeros, now you're dealing with something that's got some shape and some form to it. So, for instance, let's see, this compute packet value here. This becomes really, really simple if you have your data structure set up well and you can just parse into this data structure. If it's a literal, return the value. If it's not, which means it's an operator packet, we compute whatever the subpackets values are, and then we figure out based on the operation what thing do we do with all of these sub values and return that. So this gets really, really simple. So anyway, that's all we've got for this week. Tune in next week. Would love to see you there. Again, would love to have you on stream. Thank you, Eric, for being on stream and embarrassing me because you went straight to the smarter solution.
I learned it watching you, Floyd.
Well, I appreciate you being here and showing off your code. Invitation is still open if anybody wants to jump on stream next week, talk about their day 16, day 18, day 17, or beyond. Reach out to us on Slack, and we'll find a way to get you in and have you as a guest on the stream. Thanks so much for watching, and we'll see you guys next week.